Hello everyone, my name is Xinyu Chen. I will be discussing my research on detecting hand tremors in Parkinson's disease patients. This project is advised by Professor Zhou during this summer. To start with some background, so why is this so important to focus on Parkinson's? Parkinson's disease is a progressive neurodegenerative disorder that primarily affects movement. Parkinson's disease is called progressive because the symptoms worsen over time. The picture here explains the stages of Parkinson's disease. Initially, the effects might be subtle, such as a slight tremor or stiffness, but as the disease advances, the motor and non-motor symptoms gradually become more severe. The progression rate varies between individuals, but the degenerative nature means that without intervention, the brain's ability to control movement diminishes. In the end, walking or standing may be impossible without help, and there will be other issues like cognitive decline and communication issues. Imagine these patients cannot say a complete sentence due to a weakened facial and throat muscles, and their life is wholly dependent on caregivers. What's more, Parkinson's affects over 10 million people, and with an aging population, its prevalence is expected to increase significantly in the coming years. So why is this project important? Why accurate detection of hand tremor is needed? This is because tremors, especially in the hands, are one of the earliest and most visible signs of Parkinson's. Accurately detecting and monitoring these tremors can help clinicians adjust their treatments more effectively and offer timely interventions, improving patients' quality of life. My research aims to contribute to this by developing more precise methods for tremor detection using advanced signal processing and machine learning techniques. So my research question is how to accurately detect hand tremors based on patients' movement data collected under design environment. In this study, we collected sensing data and video ground truths for the tremor activities from 14 patients with the help of the medical professionals from Virginia Commonwealth University. For data collection, we employed the commonly used tremor rating scales. These activities include such as toe tapping, hand writing, hand movement, and so on. The data is collected using IMU devices, which are shown in picture B. IMU stands for Inertia Measurement Unit, a device that combines accelerometers, gyroscopes to measure specific forces, angular velocity, and orientation. We begin by pre-processing the data. This includes removing any erroneous data points, normalizing the data to ensure consistency across different trials, and eliminating unusable data. We then calculate the vector magnitude, which is essential for capturing the overall movement from the IMU sensors. After pre-processing, the next step is feature extraction. In this step, we separate instances of tremor and non-tremor activities. We apply the fast continuous weaklyh transform on individual instances to extract meaningful features from the time series data. The results from the fast continuous weaklyh transform are segmented into windows, enabling us to capture dynamic features over short time intervals, which is important for detecting tremor patterns. The prepared dataset is fed into the model for training. The model architecture consists of two main components, a convolutional neural network and a long short-term memory network. The CNN processes the input data, extracting spatial features, while the LSTM focuses on the temporal sequence of these features to capture any time-dependent patterns. The final output layer provides a classification result, indicating whether tremor is present or not. Once a model is trained, it's evaluated based on the F1 score, which considers both precision and recall. Lastly, the method's performance is compared with the current SOTA methods to determine how well it performs in relation to existing solutions. Let's take a look at the results of the leave one out validation for a few selected patients, represented here as P1, P3, P4, P6, and P7. In this chart, I'm comparing the performance of my method, represented by the blue and orange bars, against the current state-of-the-art method, shown by the purple bars. The y-axis represents the performance metrics, which in this case is F1 score, while the x-axis lists individual patients. Starting with patient 1, we see that my method in orange significantly outperforms the SOTA method, achieving a score close to 90%, while the SOTA method struggles with a much lower score of around 30%. This suggests that my approach is able to handle the characteristics of this patient's data much more effectively. For patient 3, both my method and the SOTA method perform relatively poor, which scores around 10% to 20%. This indicates that this patient's data might be particularly challenging to model, suggesting room for improvement in both approaches. In summary, across all selected patients, my method consistently outperformed the SOTA method, especially for patients like P1, P4, and P7. This demonstrates the robustness and reliability of the model I've developed, particularly in detecting tremors more accurately compared to existing methods. Thank you for listening to my presentation.